Welcome to The Explainer. Today we're diving into a truly revolutionary new way of building the networks of the future. And no, we're not just talking about slightly faster Wi-Fi. We are talking about building a quantum internet, a network made, quite literally, out of light.
I mean, think about that for a second. What if you could send a message so secure that the very laws of physics themselves would guarantee its privacy? Or what if you could link super-sensitive sensors all across a city to make measurements more precise than anyone ever thought possible? Well, that is the incredible promise of quantum technology, and it's exactly why we need a completely new kind of network to bring it to life.
The secret sauce here is a truly mind-bending phenomenon called quantum entanglement. The best way to think of it is this deep, almost magical connection between two particles. Once they're entangled, they are forever linked. Whatever you do to one particle instantly, and I mean instantly, influences the other, even if they're on opposite sides of the planet. This link is so perfect that you can use it to create unbreakable encryption keys. Why? Because if anyone tries to eavesdrop, the very act of looking at it breaks the connection, and you know immediately that you have an intruder.
So, you're probably wondering, if entanglement is so powerful, why don't we have a quantum internet already? Well, creating these entangled pairs in the cozy confines of a lab is one thing, but trying to maintain that incredibly delicate connection over real-world distances, that's where things get really tricky.
You see, for a quantum network to actually be useful, you've got to check 4 really important boxes. First, you need high rates. We're talking thousands of these connections every second. You need ridiculously high fidelity, which means the connection is almost perfect with very few errors. You need high efficiency, so you actually detect the signals you send. And here's the kicker. You need to do all of that over long distances. Getting 1 or 2 of these is hard enough. Getting all 4 at the same time has been the holy grail.
So what's the big bad wolf here? Well, it all boils down to signal loss. The quantum signal is carried by single particles of light, called photons, and they are unbelievably fragile. Trying to send one down a standard fiber optic cable is, and this is no exaggeration, like trying to whisper in a hurricane.
And just look at these numbers. They're brutal. The signal loss isn't a slow leak. It's an absolute waterfall. Even with the best fiber optic cable we can make, a staggering 90% of your photons are just gone after only 20 kilometers. That's about 12 miles. So trying to go across a city? Direct transmission is a non-starter. You need a totally different strategy.
So, the first big idea to solve this was actually pretty clever. Instead of trying to force one poor little photon to make the whole journey by itself, why not build the connection in shorter, more manageable segments, and then stitch them together? Think of it like a relay race, but for entanglement. So here's how this matter-based approach works. First, you create these short, entangled links between pairs of atoms, which act like tiny quantum memories. These atoms can actually hold on to the entanglement for a little while. Then, you use this really cool trick called entanglement swapping to basically daisy chain the short links together, creating one long, continuous connection.
Now, on paper, it's a brilliant idea, but in reality, hoo boy. The best systems built this way are just painfully slow. We're talking 1 or 2 successful connections per second. You could literally count them. And worse, the quality, the fidelity of that connection is pretty low, somewhere around 60 to 70%. That's like a phone call that drops every 3rd word. For anything practical, we need something way better.
And this is where the story takes a turn. This frustration led researchers to a completely different strategy. They asked, instead of relying on slow, clunky atoms, what if you could build the entire network out of the very thing it's trying to transport? What if you built it out of light itself?
And this is the key insight. It's so clever. Forget about storing the information in a particle. Here, the information is the particle's journey. You send a single photon into a special prism, and you can make it exist in a quantum superposition, where it's literally traveling down 2 different paths at the exact same time. The photon becomes entangled with its own location. It's just simpler, cleaner, and it avoids all that messy business interacting with atoms.
And because you're just using light and some simple optics, you can try to make these connections at an absolutely incredible rate. How incredible? Try this on for size.
100 million attempts every single second. That sheer volume, that speed, just completely changes the game.
Okay, you might be thinking, but hold on. Don't you still need some kind of memory to synchronize everything? Yes, you do. And this might be the most elegant part of the whole thing. The memory is just a long coil of fiber optic cable. If one photon gets there a little early, you just send it on a quick detour through the coil. It comes out a few nanoseconds later, perfectly in sync. It's a memory made of light for light.
So you put all of these all-optical pieces together, and what do you get? Well, the leap in performance is nothing short of staggering. Okay, this is the payoff. The results are just night and day. Remember those matter-based systems maxing out at 2 connections a second? The goal for this new all-optical architecture is to deliver 1,000 successful, high-quality entangled pairs every second, even over a 100-kilometer network. That's not just an improvement, that's a whole new ballgame. It's a revolution.
When you put them side by side, the difference is just so stark. The all-optical approach is hundreds of times faster and is aiming for fidelities above 99%, which is the kind of quality you need for real-world stuff. So you can see, right? The matter-based systems are fantastic for doing fundamental research in a lab, but this new method, this is what's going to build the first practical networks.
Now, let's be real for a second. This isn't going to connect New York to Los Angeles tomorrow. That kind of distance still suffers from too much signal loss. But what this technology unlocks right now is the ability to build really high-performance quantum networks across a whole city or metropolitan area, linking universities, national labs, and data centers.
And that really brings us to the most exciting part of all. This isn't science fiction anymore. These city-scale networks are actually being built as we speak. This breakthrough is what takes quantum networking from a lab curiosity and turns it into an engineering reality. It opens the door for unhackable communication, for ultra-powerful sensor arrays. The hardware is arriving. So the real question now is, what amazing things will we build with it?